Okay, good morning, CCTI AP Calculus, Mr. Pashara here. Today we're going to talk about this topic that's a little, I shouldn't say a little, it's very in-depth, but at the high school level I'll try to just give you the main ideas. Approximating area under a curve that leads us into this major topic of the definite integral, which leads us to the evaluation theorem, which leads us to the granddaddy of all, which is the fundamental theorem of calculus. The idea is simple, and from what you've read and what you've done on the computer, we should kind of understand what's happening at this point. We want to figure out what is the area underneath the curve. And we'll start off by looking at a very easy function, a parabola, and we don't have any funny business. We don't have this curve going under the x-axis, because when that does happen, the idea of area changes a little bit. But let's take a look at a function we're quite familiar with, x squared, and we're going to look at this function over the interval from 0 to 1. Okay, so I think we all would agree that this curve looks something like this. And what we want to do is we want to figure out what is the area underneath this curve, right? What is this area going to be, all this inside here? Well, what the old mathematicians realized was that we know how to take areas of things like rectangles. So the whole idea is we can approximate this area by taking a sum of rectangles. And believe me, there's a lot more to this than just that. There's things called partitions, subintervals, there's a whole lot, but I'm just going to try to give you the most basic idea, since we're not together in class too. So one of the things that you should have read is this idea of right-hand endpoints and left-hand endpoints and subintervals. If we wanted to obviously take the area using one rectangle, that would cover this whole region, but that would be a gross overestimate of what this area is. And if we broke this up into two rectangles, that would still be a gross overestimate of the area. So the way that I have this example is, let's just say we take a look at this function, x squared, over 6 subintervals. So what that means is we're going to have 6 approximating rectangles in here, and here's how we figure it out. By definition, we're told that we have something like this. The limit, as n goes to infinity, of the summation of I equals 1 to n of f of x sub I delta x is this fancy thing called the definite integral. So what this means is this delta x stands for essentially the thickness of our rectangles. And by definition, delta x is given by b minus a over n, which means we take our endpoints, subtract them, and we divide by the number of subintervals we want. So we want 6 subintervals. So in this example, delta x is going to be 1 minus 0 over 6, which is 6. And we'll work with it as a fraction, but you can work with it as a decimal. So what we're doing here is we're approximating this area based on 6 subintervals. Now keep in mind, this is not going to give us the actual bona fide area, just an approximation. The integral itself, the definite integral here itself, comes from the fact that when you sum up a finite number of these rectangles and you go off to infinity, right, after you go off n times, right? So imagine these rectangles getting so skinny. Eventually you will get the actual area. But here we're just approximating using 6 subintervals, and what we're also going to do is use, in this example, the right-hand endpoints. There's also something called right-hand Riemann sums, okay? And right-hand Riemann sums is a little bit more of the abstraction. We're not going to cover that. We're just going to jump from finding approximation of the area and then right into the definite integral itself. So that means that each of these rectangles that we're going to approximate has a thickness of 1/6. So that would be the situation. So what would these subintervals look like? Well, we would have x naught to start, that's going to be 0. X sub 1 would be 1/6. X sub 2 would be 2/6. X sub 3 would be 3/6. X sub 4 would be 4/6. X sub 5 would be 5/6. And x sub 6 would be 6/6 or 1. So you see we covered all of that interval from 0 to 1. So everyone would have a thickness of 1/6. And because we're looking at the right-hand endpoints, what that means for us is this is going to be typically an overestimate, because each rectangle is going to go a little bit higher because you're on the right-hand side, right? So this would be one of them typically. 2, 3, 4, 5, and 6. Okay, so we're looking at the right-hand endpoints of this this curve. So we're looking at all the right-hand spots. So it hits typically at the top corner of each one. Okay, so that's what would be going on here. It's not perfect. We don't have a grid, but these are your endpoints. Now we want to approximate the area, so when we sum up all these rectangles, right? So what does this mean for us? Well, the right-hand endpoints means we're going to start not at x naught, but at x sub 1, because the first subinterval, right, there's x naught, that's 1/6, right? We want the right-hand spot of it. And we go all the way until x sub 6, that would be your last right-hand spot. If we were looking for left-hand endpoints and using that estimation, we would start at x sub 0 being 0, because we want the very left, but we would stop at 5/6, because if we went to 6/6, that would be the right-hand endpoint. So what does this look like? So using the right hand, or the right endpoint, what we're saying is this Riemann sum is going to be 1/6 times the function evaluated at f of 1 plus f of 1/6 plus dot dot dot. I'm going to put the dot dot in to show that there's going to be f of 2/6, f of 3/6, f of 4/6, f of 5/6, and I'll put plus f of 1, which is 6/6. So we evaluate the function at each of those, what we call sample points. Those are the sample points for each subinterval, okay? I know there's a lot of terminology with this, but this is what's going on. Okay, so right-hand endpoints, we start at, this should be, let's see, I put an f of 1 there, that should not be an f of 1, I apologize. We have f of 6, f of 2, 6, 3, 6, 4, 6, 5, 6, and 6, 6, which is 1. So this is correct right here. 1/6 times what we have. So just get rid of the f of 1, because these are the right endpoints. Okay? So now all we have to essentially do is evaluate these in the original function. So I'll spare you the time to do that. This would be 1/6 times, we would have 1/36 plus 1/9 plus 1/4 plus 4/9 plus 25/36 plus 1. And when you add all those up and multiply by a sixth, you would get 0.42. So what this means is when you use the right-hand point of these approximating rectangles, what we're saying is the approximate area over 6 subintervals would be 0.42. Is that the actual area? No, it is not the actual area. That is the approximate area based on 6 subintervals. So how do we get the idea of what the actual area is? Well, we would have to refine this process and keep taking more subintervals. So maybe take 8 of them, or 10 of them, or 12 of them, 20 of them, 400 of them. I don't think you're going to want to write out 400 of these, right? That's why this definition is huge. Because what this is saying is over time, okay, over time, when you refine this process and you take the limit of all these approximating rectangles, eventually you are going to get the definite integral, which is the area under the curve, eventually, okay? But for us right now, we're just taking the approximation. So this is 0.42, and 0.42 is going to be an overestimate. Typically, right-hand endpoints are an overestimate. Left-hand endpoints are going to be an underestimate, okay? Let's see what the left-hand endpoints would be. So if we wanted to approximate the area by using left-hand endpoints, let's see what they would be. So now let's approximate our left endpoints. So that would be 1/6 times, now it's going to be f of 0 plus f of 1/6 plus dot dot dot, because we're going to add all these up. And then the last one is going to be f of 5/6. Remember, we don't want to use 1 or 6/6 because that would be the last point, which would be on the right. We want the left endpoints here. So once again, we would add all these function values up. We would get the following. We would get 1/6 times 0 plus 1 over 36 plus 1/9 plus 1/4 plus 4/9 plus 25 over 36. Let's see, 1, 2, 3, 4. And let's see. That would be, yep. So 25 over 36 would be our last one. And then when we go ahead, sum those fractions and multiply by a sixth, we get an answer of 0.25. So when we use the left endpoints over 6 subintervals to approximate, we're saying that our approximate area is 0.25, which is going to be an underestimate. So it's an underestimate because that's what typically left-hand endpoints do. Because graphically, this is what's going on. There's your curve, right, of x squared. So the left endpoints, this is pretty much collapsed here. The left endpoints generally look like this. 1, 2, 3, 4, 5, and 6. You see how there's space in between under the curve? That's because this is an underestimate. Okay, this is an underestimate. And you can see at the end here why we don't choose that one. That we choose that point over here at 5, 6, because over at 1, that's a right-hand endpoint, we don't want it. So, what we figured out was the right-hand endpoint gives us an approximation of 0.42. The left endpoints give an approximation of 0.25, so it's an underestimate. So again, what is this definition that you see in your book tell you? It tells us that when we take together the left and right endpoints and essentially drag them out far enough and make the rectangle skinny as possible, you will get the eventual total area. And I'll show you now how we do it. We're going to skip the Riemann sum part with the abstractions, and we're going to go right to something called the evaluation theorem. Now, the evaluation theorem leads us to the fundamental theorem of calculus, which you've probably already seen at this point by doing your work on the computer and reading your textbook, hopefully. The evaluation theorem is going to be your best friend, as I told you in the email, because the evaluation theorem says this: if you want to integrate a function over an interval, essentially what we do is we take the antiderivative at f and the antiderivative evaluated at a, and that will give us the area. And this is actually what we call fundamental theorem of calculus part 2, actually. But for now, we just call it the evaluation theorem. So that makes our life easier because you know how to evaluate an indefinite integral. Now we're just going to slap numbers on it. So let's actually take a look at what the exact area of x squared equals x squared over the interval from 0 to 1. Let's find out what that actual area is. So that means now we can write this thing as an indefinite integral. So this is the indefinite integral from 0 to 1 of x squared dx. So what this means is we take the antiderivative of x squared, which is x cubed over 3, and we evaluate it at x equals 1 and x equals 0. So what does that mean? That means we have 1 cubed over 3 minus 0 cubed over 3, which is a third. So the actual area is 1/3 or 0.3 repeating. So you see how the actual is right strictly in between the left and the right hand endpoints approximation. And that's how it works. So this is pretty nifty. So what I did for your homework is you had to go through and use the left endpoints and right endpoints. What I did for you as a bonus, I went through and I showed you how to use the evaluation theorem to get the actual area so you could practice. And that'll be one of our upcoming topics. How do we go ahead and do more sophisticated definite integrals, like when we have to use substitution? Because we can't just leave these same bounds here, we actually have to change those, but that'll be for another day. I'll show you how you do that, and I'll show you the cheat version of that. Okay? So generally, right endpoints are an overestimate, left endpoints are an underestimate. But here's an interesting thing to think about. Say, for example, you have a curve like this, right? So the area, there's some area that's underneath that we considered, if you want to think of a negative in some way, right? So what does that mean when we use the approximating rectangles? The approximating rectangles is actually just giving us the area that's the positive part. So your answer really, when you sum up using the Riemann sum, is you're going to get the net average between what's on top and what's on bottom. So on an integral like this one, if this was your actual graph and you had equal area on top, equal underneath, this integral would actually balance out to 0. That would be the change, right? You have so much positive, so much negative there the same that they essentially cancel each other out. So we just have to be careful of that idea with approximations is that, well, if everything is above the x-axis, that's your exact idea with the approximating rectangles. However, when your curve dips below the x-axis, you could think of it as negative area in a way, even though there really is no such thing. So your rectangles are actually going to sum out to tell you what is the positive amount of area, the area above the curve. That's what your answer actually is. Okay, so hopefully this video helps you go ahead and do the approximating part. I will do another video with you guys shortly on the second worksheet, just so you have some extra guidance on that, okay? So again, the big idea here was approximations, and using this definition then to get to the definite integral. And once we have the definite integral, we have this idea of the evaluation theorem, which leads us to the fundamental theorem of calculus part 2. Okay? So until then, I hope you guys are healthy and well and safe. Be good. Call or email if you have any questions. And I will see you guys shortly on another video.